Could you imagine a scenario where you would want to solve multiple linear system problems with the same matrix A? Well, what would multiple linear systems problems be if you had the same matrix? What would change? Yeah. So method 2, we're going to call LU factorization. If we have an entire set of non-singular linear systems problems with the same matrix A, i.e., what would it mean to have a set of these things? And then I literally have like tens of them. What would that mean in R? Maybe you call them P of them. What would that mean in R condition? When would that arise in the particular experiment we set up? Well, what was the original experiment? So I have a ball, I drop it, I sample it at time 3, 3.3, 3.6, and then at those times, what do? I measure 3 different heights, right? And the vector B that we started with stored those 3 different heights. What would it then mean if I had many, many linear systems problems based on the same A?
Oh, you do that like 3 more times.
Yeah, you do that like 70 times with 70 different heights, right? Yeah. And every single time in that situation, we would then need to do the exact same representation because all of these wouldn't have changed, right? All of these transformations wouldn't have changed, but I would have to store them and done all the calculations on my independent B's, right? Do you see the cost there? It means that I have to freaking store all this data. That's one thing. And then the second thing is I have to apply all those transformations for all of my matrix B just to get it in the form with the U and the corresponding Y, right? So in this case, we might pre-process A by factorizing. And the way that we're going to factor this is L times U. Can you guess what U would be? Upper triangular. Anybody guess what U would be? L, sorry. Lower triangular. Do you want me to treat you like novices or like professionals? Okay, so then no permutation matrices is necessary. Novices, all you need to do, we will assume that every matrix that you'll ever work with is regular. You know what a professional would say, right? There's something called the partial, depending on if you want to do full partial pivoting or full pivoting. Partial pivoting is you're allowed to switch rows around. And that actually shows up numerically. We'll start with this assumption. We'll call this method 2 because we're just introducing. And in this case, it just so happens that these matrices, you can, if you multiply all those together, do you know what happens if you multiply a sequence of shear matrices together? What type of matrix you get? Lower triangular. What were you going to say? Yeah. And we'll do this. We're actually going to do this whole thing. Yeah, go ahead. It's not strictly lower triangular. It's actually, these are just shear matrices, they're actually called unit lower triangular because yeah, we're going to do this in lesson 15, actually. We're going to get to this, right? But the reason I want to tell you this is I'm about to give you an algorithm. We call the first algorithm we worked with called backward substitution, right? Can you guess which ones we haven't done yet? Forward substitution. Backward substitution uses upper triangular matrices, starts with the bottom row because that has mostly zeros, and then works backwards upwards, right? Yeah. Can you guess what forward substitution does? Lower triangular matrix, start with the first row, start with that first entry, and then work backwards, or work forward, sorry, down to the bottom, right? You might ask yourself, well, why would I ever worry about forward substitution? And the answer to the question actually happens right here. If I'm going to solve those things, such that every single time this happens, here's the claim that we can do. It's actually pretty freaking creative, to be honest with you. So the whole idea is I wanted to solve a times any general thing that I wanted to generate there. We'll call it xi, right? I guess I could call it j. And this is supposed to be b sub I, right? But what did I know about a? Well, the claim is we're going to be able to factor a. It's not easy to do. It takes pre-processing, it takes plans, and right now we're associating those together. What do you know about matrix multiplication? Does it matter which order you associate in? So it's kind of a theorem that we've at least mentioned out loud, I think. What if you called this thing y? And maybe you call it y sub I. Yeah, I should probably erase the I so you're not confused right now. Why am I putting a sub I on that thing? If you only had to solve a linear systems problem once, would it be worth factorizing? No. Not necessarily, right? Like if all I have to do, like if let's say that I took 18 times x and I set that equal to 81. Okay, how could you solve that problem? Just divide, right? But if I had 50 different numbers here, you might say to yourself, well, why don't I get all the factors of this thing? And then whatever factors are over here, I can cancel them out and make it easier. This is not an LU factorization. That's called a prime factorization. But the idea is, with a little bit of extra work, I might save a lot of savings over the 15 problems that I work on, right? And the same thing is true over here. If I work on this problem and I do a little bit of pre-processing, what ends up happening is, first I would solve a lower triangular problem. We don't know how to do that yet. Can you guess what the solution is going to be called? What the algorithm is going to be called? Forward substitution. Once I have my forward substitution, which is going to produce my y vector, what is it that I actually cared about? My x vector. Well, the solution to the x vector, once I get this y vector, if I put it over here, do you recognize this? This is upper triangular. This will be the exact y that came out of the process in method 1, right? And then at the end of the day, what am I going to get? Backward substitution, which means I've translated every linear system problem into a sequence of 2 related linear systems problems, one of which requires a forward substitution, the other one which requires a backward substitution. What's the one caveat? What's the one thing I need to be able to do? Factor it. Well, guess what you know how to do? Well, you don't know you know how to do this yet, but in about 3 days you'll know how to do this, right? So could you guess, if this is a strategy, and this strategy is supposed to be applied to many, many linear systems problems, what thing would you need to be able to do in order to apply this strategy? What thing do you already know how to do? Backward substitution. You would also need to know how to do, and then, if you knew how to do both of those, and you could factorize, then you'd be good and dandy, right?